Normally I want these videos to give you enough information that you can, let's say, hit the ground running, so you get to class and you can right away start working with it. It's not going to be quite like that for this one, but I do want to lay some groundwork. When we talk about organic reactions, they're going to look a little bit different. They're going to be treated a little bit differently than, say, the traditional reactions. So what do we mean, or what exactly is our focus with an organic reaction? Particularly, it's going to be the functional group. So an organic reaction is nothing more than converting from one functional group to another functional group. So we don't need to worry about the synthesis, decomposition, double displacement, single displacement stuff that we've had before, although we will have various types of organic reactions. We typically write them differently as well. We still have a reactant side, product side, and an arrow, but we tend to emphasize the organic part. And then the other things that are necessary, be it the other reactant, the inorganic part, or a catalyst or heat, that's going to be written on the arrow, and we'll sometimes talk about that as being the reaction conditions. And we generally don't balance them. So even if they're written so that makes no sense in terms of the balancing, we don't worry about it. And if I give you an example of one like that, and here's an example of an organic reaction that emphasizes all of those points. We were going from an alkyne to an alkane, although you probably wouldn't want to do that very often. In order to do that, we're taking 2 moles of H2, even though I only have 1 written down, and then the PT, the platinum, is there as a catalyst. So it's necessary for the reaction, but it's a catalyst. Now you'll notice that I don't account for all of the hydrogen that gets added. I don't account for what happened to the platinum. It's just a catalyst. But that's how I would write an organic reaction. Okay, now I said there were various types of reactions that we're going to be looking at. And we're not going to focus in so heavily on those terms as you would have had, say, for a single displacement or a double displacement. But we are going to use various terms, and it's helpful if we understand what's happening during a reaction, even if we don't get down to the nitty-gritty. So an elimination reaction, obviously, is something being taken away. Again, converting from one functional group to another functional group. In this case, I'm eliminating water. If you don't see the water coming out because it's the OH that's the most obvious, but the carbon next door to the carbon in the functional group started out with 2 hydrogens, now only has 1. So water has been eliminated. And again, you'll see the reaction conditions on the arrow. We'll deal with those in more detail another time. There's a substitution reaction. Something comes out, something else goes in to take its place. So in this particular one, I have substituted a chlorine for the OH group. So I've converted from an alcohol to an alkyl halide. Oxidation is going to be a big one for us. And the large look at oxidation is going to be going from something like an alkane or an alkene, a straight hydrocarbon, to an alcohol, to an aldehyde or perhaps a ketone, depending on where the carbon of the functional group is, to an acid, if that's possible, and it could go all the way to carbon dioxide. However, I want to stress at this point that generally what we want to do in terms of converting from one functional group to another functional group is we're going to be focusing on those middle 3 a lot. So we're going to oxidize from an alcohol to a carbonyl, either the aldehyde or the ketone, possibly all the way to an acid. Sometimes we'll actually want to go backwards. So we'll start with an aldehyde or a ketone and we'll reduce it, is the other term, back to the alcohol. Rarely do we reduce an alcohol back to the alkane. It's just not very useful to us. I want to think about oxidation though in terms of how many bonds we have to the carbon. So I start out with how many bonds we have to an oxygen. I start out with no bonds to an oxygen, then I have 1, then I have 2, then I have 3 bonds to oxygen, all the way up to carbon dioxide with its 4. Addition is just adding something on. It would be similar to the synthesis type reaction that you would have learned in another time. Here, what I've done is I've taken the alkene and I've added something across the double bond. Both carbons of the functional group added something, but it's only the chlorine that shows up. So it's important to look a little bit beyond there as well. Okay, now some reactions are going to show preference. We're not going to get into the details right now. We'll get into the details in class. We'll give it a name. We'll talk about how we can identify it. But the preference comes from the fact that if I look at that addition reaction, I lined up, or I could line up the hydrogen chloride across the double bond in this fashion, and I would get this product. On the other hand, I could spin one of those molecules around and line up the hydrogen chloride in the other direction. Not the normal way we write hydrogen chloride, but perfectly acceptable in terms of molecules colliding to have a reaction. And in which case I would get the chlorine on a different carbon atom. Now it turns out that this bottom one, the second one, is more likely to happen, and we'll talk about the reasons for that another time. At this point, all I want you to be aware of is that some reactions show preference, and you will be expected to know what the preference is. Not right now, but eventually yes. When I see a mechanism, you're not going to generally be expected to know the mechanism. I find it helpful. It helps me understand why things happen if I understand what exactly is happening. But if I start out with a alkene, it's going to be our first reactive group that we're going to look at a bunch of reactions for, and I take a hydrogen bromide. Now I've written it sort of backwards for our point of view, simply because, similar to the previous example, that's the preference that's going to be shown. Now what's going to happen is I've got electrons in the double bond that are semi-available, and I've got electrons in the hydrogen bromide that I could make available as well. Why they're available is a story for another time, and we'll come back to that hopefully at another time. But what happens is the double bond electrons move from being shared between those carbons to somewhere else on those carbons. And then the electrons in the bond between hydrogen bromide, they also move. And those arrows are representing single electrons moving a certain way. So out of the bond and into a new space where they happen to be able to share between carbon and bromine, carbon and hydrogen. Now we would never write it like that. It looks kind of silly, but it is how the bonds end up forming. What I would typically end up writing is this. Now again, that hydrogen that was added across the double bond is a little harder to see, but it is definitely there and we have to be aware of it. Okay, at this point, I know it's a whirlwind tour and all we're trying to do is get you ready, sort of prime the mind for what's going to be happening in class. And you are not expected to be able to do this at this point, but by the time we have taken care of the specifics of reactions and perhaps some of the details, you should be able to identify where a reaction is going to happen. You should be able to draw the products for them. And you should also be able to be given a set of products or a product and asked, well, how could I make that? What could I use to make that particular reaction, or sorry, that particular product? What kind of reaction would you use? So hopefully it sounds pretty simple, and at the end of the day, organic chemistry and doing the reactions like this kind of is. A lot of people will disagree with me on that one, but if we start thinking about big picture things, organic reactions are not all that difficult because they follow a similar pattern every single time. But we'll try these out in class.